It is possible to reconnect a 6-lead 480 volts 100 horsepower motor from a part winding starter to a standard 3-pole full voltage non-reversing starter. The materials required are a multimeter, electrical tape or heat shrink, and wire nuts, which are optional. Firstly, safety first. Disconnect power to the motor and verify with a multimeter that it is de-energized. Lock out and tag all power sources. Secondly, identify motor terminals. Locate the 6 terminals on the motor and tag them as follows, using a multimeter for continuity testing. Tone T2 and T3 are main power terminals. T4, T5, and 6 are start capacitor terminals. Thirdly, disconnect starter wires. Disconnect the wires from the part winding starter. Fourthly, connect main power leads. Connect 3 of the main power terminals, tone T2 and T3, to the 3 terminals on the full voltage non-reversing starter. Fifthly, reconnect capacitors. Determine which 2 start capacitor terminals, T4 and T5, connect to the main power terminals. Use the multimeter to check for continuity between the start capacitor terminals and the main power terminals. Connect these 2 start capacitor terminals to the zone and S2 terminals on the full voltage non-reversing starter. Sixthly, insulate unused terminals. Insulate the remaining start capacitor terminal, 6, and any unused terminals on the motor with electrical tape or heat shrink. Seventhly, test motor rotation. Power up the motor and check its rotation direction using a voltmeter or strobe light. If the rotation is incorrect, swap any 2 of the main power connections, tone T2 and T3. Additional notes include capacitor ratings. Ensure that the start capacitors used in the full voltage non-reversing starter are rated appropriately for the motor's power and voltage. Also, wire sizes. Use wire sizes that are rated for the motor's current draw and the length of the run. Safety precautions. Always follow proper electrical safety procedures and wear appropriate personal protective equipment when working on electrical equipment. When dealing with electrical motors, understanding their connections is crucial for efficient and safe operation. A 6-lead 480 volts motor presents a specific wiring configuration that needs careful attention when transitioning from a part winding starter to a full voltage non-reversing starter, often abbreviated as FVNR. Firstly, let's discuss the basics of motor connections. Motors with 6 leads are designed to offer flexibility in how they are connected to the power supply, typically allowing for different voltage configurations. In the case of a 480 volts motor, these leads need to be connected in a way that matches the supply voltage to prevent damage and ensure optimal performance. The part winding starter is a type of motor starter that applies voltage to only part of the motor winding during startup, reducing the inrush current. This method is commonly used to mitigate voltage dips in the power supply system during motor starting. However, when the utility has approved cross-the-line starting, which is also referred to as full voltage starting, a full voltage non-reversing starter can be used. This type of starter applies the full voltage to the motor windings immediately upon startup, providing maximum torque but also drawing a higher inrush current. The transition from a part winding starter to a full voltage non-reversing starter requires a reconnection of the motor leads. The 6 leads need to be identified and connected in a specific configuration to ensure the motor operates correctly at 480 volts with the full voltage non-reversing starter. Here's a step-by-step guide on how to accomplish this. Firstly, safety is paramount. Before beginning any electrical work, disconnect the power supply to the motor at the circuit breaker or disconnect switch. Use a multimeter to verify that the motor terminals are de-energized. Implement lockout-tagout procedures to prevent accidental re-energization of the circuit while you're working on it. Secondly, identify the motor leads. The 6 leads are typically labeled as tone T2, T3, T4, T5, and 6. Use a multimeter to identify the corresponding leads. In a typical 6-lead motor configuration for high-voltage operations such as 480 volts, tone T2 and T3 are connected to the power supply, while T4, T5, and 6 are connected together, often referred to as a wire-star connection. Thirdly, disconnect the existing part winding starter wiring. Carefully disconnect the wires from the part winding starter terminals. Make sure to label each wire as you disconnect it to avoid confusion during reconnection. Fourthly, prepare for the full voltage non-reversing starter connection. With the part winding starter wires disconnected, prepare to connect the motor leads directly to the full voltage non-reversing starter. The full voltage non-reversing starter will have 3 terminals, one for each phase of the 480 volts power supply. Fifthly, connect the motor leads. Connect motor leads turn T2 and T3 to the 3 terminals in the full voltage non-reversing starter. The specific terminals to which these leads are connected may depend on the rotation direction desired. If the motor rotates in the wrong direction after the initial connection, you can swap any 2 of these leads to reverse the rotation. Sixthly, make the Y connection. Connect motor leads T4, T5, and 6 together. This creates the Y or star connection required for high voltage operation. Use a wire nut or other approved connector to ensure secure and insulated connection. Seventhly, insulate and secure connections. After making all the connections, carefully insulate each connection with electrical tape or heat shrink tubing to prevent shorts or ground faults. Ensure that all connections are secure and that there are no loose wires. Eighthly, verify the wiring. Before re-energizing the circuit, double-check all wiring connections to ensure they are correct and secure. Use a multimeter to check for continuity and insulation resistance to identify any potential problems before applying power. Ninthly, test the motor operation. After verifying the wiring, remove the lockout tagout and re-energize the circuit. Observe the motor's operation to ensure it starts and runs smoothly. Check for any unusual noise, vibration, or overheating. If the motor does not start or runs erratically, immediately de-energize the circuit and recheck the wiring. Tenthly, adjust for rotation if necessary. If the motor rotates in the wrong direction, de-energize the circuit and swap any 2 of the tone T2 and T3 leads at the full voltage non-reversing starter. This will reverse the motor's rotation direction. 11thly, final inspection. After confirming that the motor operates correctly and rotates in the desired direction, perform a final inspection of all wiring connections and insulation. Ensure that everything is secure and properly installed. Also, consider the following important factors. Firstly, wire size selection. Ensure that the wire size used for the connections is appropriate for the motor's full load current rating. Refer to the National Electrical Code, NEC Table 430.250 to determine the appropriate wire size based on the motor's horsepower and voltage rating. Secondly, overcurrent protection. The full voltage non-reversing starter should include appropriate overcurrent protection devices, such as fuses or circuit breakers, to protect the motor from overload in short circuit conditions. Refer to NEC Article 430 for guidance on selecting the appropriate overcurrent protection for the motor. Thirdly, grounding. Ensure that the motor frame and starter enclosure are properly grounded in accordance with NEC Article 250 to provide a safe path for fault current in the event of a ground fault. Fourthly, starter size. Select a full voltage non-reversing starter that is properly sized for the motor's horsepower and voltage rating. The starter should have a horsepower rating equal to or greater than the motor's horsepower rating to ensure reliable operation. Fifthly, enclosure type. Choose an appropriate enclosure for the full voltage non-reversing starter based on the environmental conditions of the installation location. For example, if the starter is installed outdoors or in a wet location, use an M4 or 4X enclosure to protect it from moisture and corrosion. Sixthly, local codes and regulations. Ensure that all wiring and installation practices comply with local electrical codes and regulations. Consult with a qualified electrician or electrical inspector to ensure compliance with all applicable requirements. Seventhly, documentation. Keep a record of all wiring changes and modifications made to the motor and starter. This documentation will be helpful for future maintenance and troubleshooting. This includes labeling wires appropriately. Eighthly, motor nameplate data. Always refer to the motor nameplate for critical information such as voltage, full load current, horsepower, and service factor. This information is essential for selecting the appropriate wiring, overcurrent protection, and starter size. Ninthly, torque requirements. Consider the motor's torque requirements when selecting a full-voltage non-reversing starter. Full-voltage starting provides maximum starting torque, which may be necessary for applications with high inertial loads or demanding starting conditions. Tenthly, maintenance. Implement a regular maintenance program for the motor and starter to ensure reliable operation and prevent downtime. This includes inspecting wiring connections, checking for signs of overheating or corrosion, and testing the operation of the starter. 11thly, troubleshooting. Develop a systematic approach to troubleshooting motor and starter problems. This may involve using a multimeter to check voltages and currents, inspecting wiring connections, and testing the operation of the starter components. In summary, reconnecting a 6-lead 480 volts motor from a part winding starter to a full voltage non-reversing starter requires careful attention to wiring connections, safety precautions, and compliance with electrical codes and regulations. By following a step-by-step guide and considering important factors such as wire size, overcurrent protection, and grounding, you can ensure the safe and reliable operation of the motor. Additional considerations for reconnecting a 6-lead 480 volts motor. Firstly, understanding motor winding configurations. 6-lead motors are typically designed to be connected in either a Y, also known as star, or delta configuration. The configuration determines the voltage and current relationships within the motor windings. For 480 volts operation, the motor is typically connected in a Y configuration, where the voltage across each winding is lower than the line-to-line voltage. Secondly, impact of full voltage starting on motor life. While full voltage starting provides maximum starting torque, it also subjects the motor windings to higher stress due to the inrush current. This can potentially reduce the motor's lifespan compared to reduced voltage starting methods such as part winding starting. However, modern motors are generally designed to withstand the stresses of full voltage starting, especially in applications where it is permitted by the utility. Thirdly, surge protection. Consider installing surge protection devices, SPDs, at the motor and starter to protect against voltage transients and surges that can damage the motor windings and starter components. SPD can help extend the life of the motor and improve system reliability. Fourthly, harmonic distortion. Full voltage starting can contribute to harmonic distortion in the power system, especially if multiple motors are started simultaneously. Consider using harmonic filters or other mitigation techniques to reduce harmonic distortion and improve power quality. Fifthly, energy efficiency. Evaluate the energy efficiency of the motor and starter combination. Consider using energy-efficient motors and starters to reduce energy consumption and lower operating costs. Also, consider using variable frequency drives, VFDs, to optimize motor speed and torque for varying load conditions. Sixthly, motor cooling. Ensure that the motor has adequate cooling to prevent overheating, especially during periods of heavy load or high ambient temperatures. Check that the motor's cooling fan is operating properly and that there are no obstructions to airflow around the motor. Seventhly, vibration analysis. Perform periodic vibration analysis on the motor to detect potential problems such as bearing wear, misalignment, or imbalance. Vibration analysis can help identify and correct problems before they lead to costly downtime. Eighthly, insulation testing. Conduct regular insulation testing on the motor windings to assess the condition of the insulation and detect any signs of degradation. Insulation testing can help prevent motor failures and extend the motor's lifespan. Ninthly, thermography. Use thermography to inspect the motor and starter for hotspots or other signs of overheating. Thermography can help identify loose connections, overloaded circuits, or other problems that can lead to motor failure. 10thly, load analysis. Perform a load analysis on the motor to ensure that it is not being overloaded. An overloaded motor can overheat and fail prematurely. Consider using a larger motor or reducing the load to prevent overloading. 11thly, environmental conditions. Consider the environmental conditions at the installation location when selecting a motor and starter. For example, if the motor is installed in a dusty or corrosive environment, use a motor and starter that are designed to withstand those conditions. The transition from a part-winding starter to a full-voltage non-reversing starter on a 6-lead 480 volts, 100 horsepower motor represents a significant change in how the motor is controlled and operated. It's important to carefully assess the implications of this change and to ensure that all necessary precautions are taken to protect the motor, the power system, and personnel. By following best practices for wiring, overcurrent protection, grounding, and maintenance, you can ensure the safe, reliable, and efficient operation of the motor for many years to come. This includes thoroughly reviewing the motor's specifications, the site's electrical infrastructure, and the applicable codes and standards before making any changes. This comprehensive approach will contribute to a successful transition and long-term performance.